So, hi everyone, welcome to our weekly seminar at Institute of Astrophysics in Forth. And today we have the pleasure to have with us Dr. Hendrik Müller, since he recently defended his PhD thesis. And let me introduce Hendrik. So he studied mathematics and physics in Göttingen, and joined the Max Planck Institute for Radio Astronomy in Bonn in late 2020 for his PhD. And he completed the PhD last June, as I said. So during the PhD, Hendrik worked under the supervision of Dr. Andrei Lobanov on novel imaging algorithms for VLBI. And he will tell us more about one of these methods during the talk. Hendrik has also recently received the prestigious Jansky Fellowship, and he will move in January to the NRAO in Socorro, New Mexico, where he will work on imaging and calibration tools for the next generation VLA using artificial intelligence application. So we are excited to learn something about this. So thanks for being with us. The floor is yours.
Yeah, thanks. Thanks for the nice introduction, and thanks for giving me the opportunity to talk here. Yeah, we developed different approaches. I will talk about one of them, which offers a couple of new perspectives on how to do VLBI imaging with forward modeling methods. But let me first motivate the whole thing a bit. Like, we are really in very exciting times when it comes to VLBI imaging. And when it comes to VLBI science in general, like, we have these new instruments planned, proposed, or in several stages of coming up, sometimes in the future, such as the NGHT and the NGVLA, and they will for sure bring groundbreaking new results, like unraveling the connection between the jet and the black hole, or even mapping the accretion flow, if that may become possible with the HT at some point. It's just important to note that these are very expensive new arrays that then also need to be accompanied with new data analysis techniques that are equally sophisticated to actually achieve these high goals. And I mean, I think I can go over this pretty quickly. The clean algorithm is, of course, the absolutely de facto standard in our field. Like, it's fair to say that 97 or 99% of people in VLBI are using this. But there are actually several issues with clean, and the main issues with clean are kind of caused by the fact that the modeling with the delta component is not physical. And clean is an inverse modeling approach compared to forward modeling approaches that are much more flexible. And clean does not process any kind of reasonable prior information. One of the consequences can be seen here in the upper panel, that the clean model and the clean image is not the same. I always denote the clean model just a set of delta components, and when we look at the Fourier transform of the delta components, then we see that the dominating feature is this kind of band-like feature in a Fourier domain, which is not covered by any kind of observing points. It's a bit worrying. While the clean image, once we have convolved our set of delta components with a beam, does not fit our data anymore. And this leads us to a couple of limitations that we need to think about. Like, modeling with delta components introduces this conceptual issue that I just described, that the model and the image are not the same. This also could introduce big biases during the self-calibration procedure. And of course, it limits our resolution because we're limited to the clean beam resolution. We see sometimes additional artifacts such as negative fluxes, extended emission, where we don't expect extended emission. The inverse modeling approach, which is inherent to clean, just limits our scope of where we can use the algorithm, because not all problems could be formulated as a convolution. And even if we start to do dynamics or we start to do polarimetry, there are, of course, fixes to do that in clean, but these are already workarounds. So when you do polarimetry, you basically have to clean in all 4 Stokes bands, but you cannot easily produce a deconvolution problem for which the solution would be the complete polarized image already. And a good prior phase calibration is essential for that to get the whole procedure of cleaning and hybrid imaging started. But the biggest problem, in my opinion, is that it remains strongly supervised and hard to reproduce. It's really biased by who is using clean and where he sets or he or she sets the windows, what are the taper, what are the weights that we adapt, how do we flex the data, and these are all kind of parameters that are changed interactively during the procedure of doing imaging and self-calibration. And when we're looking at the needs of future instruments, for example, I will now look in NGHT, not so much in the NG-VLA. We deal with extreme sparsity, at least for global VLBI experiments. We want to interpolate actually into the gap, and when we want to interpolate accurately into the gap, we have the problem, and the model is not equal to the image, that there is no really reasonable interpolation scheme. We want to achieve super resolution, so we want to get better than the limited resolution by the clean beam, and we already have proven that this is possible. Yes, typical extensions to the classical imaging problem already require clean to go to sometimes some kind of messy workarounds. It can be pretty much done much more simpler and forward modeling techniques. And in the end, we want to come up with something which is much more unsupervised. So, but when someone would now think of what do we want to do in the future, like when we sat down on what are the goals that we want to achieve with new algorithms, we come up with a very long wish list. We want to achieve super resolution, high dynamic ranges, which means sensitivity to extended emission. It should be flexible, easy, adaptable. It should, if possible, be a robust image that probably also gives us some kind of uncertainty and quantification. But at the same, simultaneously, we wanted to be fast. We wanted to be unsupervised and unbiased. And we see that we came up with these kind of RML images that are achieving super resolution in a very flexible way, and they're super fast, but cannot solve all of these wishes. The next thing that people came up with by using algorithms that actually are very successful in reconstructing high dynamic range, super resolving images. They also given us a robust estimate, but they're not that fast, and complete Monte Carlo chain iterations really take a lot of time and a lot of computational resources. Then we identified this multi-objective and multi-scale imaging, which actually go directly in the other direction of constructing something that is as unbiased as possible, as unsupervised as possible, and still remains fast, nearly real time to apply. And like the newest player on the market is, of course, artificial intelligence, where many people have the hope that artificial intelligence probably solves the scaling problem of clean. So the upscaling to very large data sets can be done much more easy. We actually we have performed a lot of different comparisons in the past and a lot of different challenges, but the main take-home message from that is that clean variants will not help us out. Not changing the way it's going to multi-scale clean is not really overcoming the limitations of clean in its fundamental. So we either need to do something, we need to do major fixes to the inverse modeling strategy, as has been done, for example, for uClean, which was a couple of months ago published for the STIX instrument, or we need to completely change the paradigm towards forward modeling. And the most widespread used forward modeling technique is, of course, RML, but the same arguments on this slide also to some degree apply for maximum entropy or Bayesian techniques. So we have an objective functional or an optimization functional that we want to minimize. It consists of a couple of data terms, for example, the visibilities, amplitudes, closure phases, closure amplitudes, and a couple of regularization terms, in this case, the total flux, L1, L2, total variation, total squared variation, or entropy. And we see this typically gives us excellent super resolving images, and a forward approach that is very flexible. For Bayesian techniques, it's very similar. You would have a couple of likelihoods and a couple of prior terms that you want to combine with different weightings. But you only get to these very nice images if your hyperparameters, and with hyperparameters, I mean all these weighting parameters, alpha, beta, gamma, delta, epsilon, and so on, are chosen correctly. So the one feature that is still missing here from all the approaches is an unsupervised analysis that really talks to the multimodality of the problem. With multimodality, I just mean the fact that there are different local minima. So there are definitely more than one physically reasonable image structure that we can fit to our data. And this will lead us to make all these algorithms simple enough to be applied in practice. Because while we have seen in almost all the challenges, and we have seen in EHT reconstructions, that the forward modeling approaches are way too superior to clean, they're still not the standard in imaging. And one of the points that is talking against them is actually that the learning curve is quite high, and you need to find all these parameters. So it's really not that simple to apply in practice. And this is where this kind of work started, and where we started to look into this weighting problem with from different perspectives. The oldest and first one that was discussed is a constraint minimization. So we want to balance some data terms like chi-squared. So on the slide before, the data terms were always denoted by an S by me, and some penalty terms. In the constraint minimization, we would just say, okay, along the line of all possible image structures that have a chi-squared that is equal to 1 or in the range of 1, we want to just minimize the penalty terms. That has been intensively studied in the 80s and the 90s, and just currently has in the context of dynamic reconstruction some revival. Basically, you would minimize the whole thing by an SQP squared programming algorithm. The more standard version that almost everyone is using, or not only in VLBI, these kind of methods, of course, apply to a much wider range of applications. You would just weight them, and then you would have to find the correct weighting parameters. The idea is by just minimizing the weighted sum of both of the data term and the regularization term. Both terms would be small. The small data term would mean that we are actually fitting our data. The small regularization term means or measures how feasible this solution is. And there are, of course, many different variants. There are also a lot of variants in the direction of multi-scale algorithms, in the direction of wavelets. You would do the minimization with something like conjugate gradients is LBFG minus B, which is a Newton type variant, or FISTA, FISTA is fast iterative soft threshold algorithm, which would apply for an L1 regularization term. But there are two different and way less explored variants of looking into this problem of balancing data terms and penalty terms. One of them is looking into multi-objective optimization. In this sense, we don't want to balance them, but we look for all the best compromise solutions along actually an array or a vector of different objectives that we want to optimize, and we're optimizing along the data fidelities and the penalties. That led us to the development of MOAT, and there the problem is a bit more complicated, so we cannot rely on gradient descent or even proximal point methods. So we have to do the optimization by an evolutionary algorithm. And a fourth version of looking into this problem, which is just kind of in the process of being studied, is that we can also see the best image as the best strategy in a cooperative game where the players are actually the different objective functionals. This is called the Shapley multi-objective problem, and again would need some optimization by evolutionary algorithms. So let me focus on MOAT a bit. What did we do in the past when we had RML-like problems? Well, we just changed the regularization parameters and we tried them out on synthetic data. But now you see when you plot the scoring of the data terms versus the scoring of the regularization terms, and you change the parameters, the hyperparameters to more favor the regularization terms, you will end up somewhere down to the bottom right of this plot. If you change the weight or the balance more to the data terms, then you would end up somewhere to the top left. And in all the intermediate cases, you will end up somewhere in between. But what you basically do, this is a grid search for a hypersurface of solutions. And this hypersurface of solutions we can also identify with the Pareto font, which I will talk later on. So this is a grid search by multiple optimization problems. We have one combination of parameters. We would run the optimization problem. Then we change our initial parameters. We would run the optimization problem again and go on in this sense. This is clearly not ideal. A complementary approach would be to try to sample this hypersurface from the begin on by free floating points. So we would like to come up with a set of solutions as a result of a single optimization problem. Now, the result of the optimization problem is not a single image anymore, but it's a set of all the images that are lying in this so-called Pareto front. And this brings us to multimodal or multi-objective optimization, which can be seen as the next generation of parameter service. Okay, to break down the...
May I ask something?
Sure.
So can you please go to the previous slide?
Sure.
So just for me to understand, so in this case, you're optimizing, so the features that you have are your images. So what you're trying to minimize for is the image itself, given the 4 different schemes that you showed before. And also the parameters in the forward model? Or are these set?
Yes. When you would do the classical RML approach, you would just minimize for the image. Mm-hmm. And you would do that for a lot of different parameter combinations. And every point in this plot corresponds to a single image, right? Right. And now we are trying to reformulate this problem. Now we don't want to just solve for the images, but we want to solve for all images that would show up in a parameter survey, but only as one optimization problem, right? So the result of this optimization is much more high dimensional.
But still, you don't optimize for the hyperparameters as well. You optimize for the features, for the images.
Yes.
Okay, thank you.
Okay. The concept that is working here is Pareto optimality. So actually, that's an image from Wikipedia, but I think it's explaining the concept quite well. If this blue area would be the area of all possible solutions, then the Pareto optimal solutions would lie in this red area, in this red surface. It tells us when the further optimization along one of the objective terms, when we have multiple objective terms, necessarily has to worsen another one, then we call this solution a Pareto optimal solution. Now, the problem is that this is not so easy to minimize because we don't have gradient. So we need to come up with something gradient free, and the easiest or one of the most natural solutions would be the genetic algorithm. In a genetic algorithm, you would start with a series of genes or genomes in an initial population. Then you randomly mutate them. You introduce some crossover from the parent population to the childhood population, and then you go to the next iteration. And the point why this is an interesting concept is because a genetic evolution can be interfaced with something that is called the archetypal model, where you have different protected neighborhoods from each other within the population. This preserves the diversity among the solution. So to make it a bit more clear, we consider the typical RML function that I showed you at the beginning, right? With all these different data terms, with all these different regularization terms. And now we reformulate it as 7 different objectives. In every objective, the data term would appear, but additionally, we add some of the regularization terms, or in the last case, we don't add any regularization terms. Now, we are not solving the problem that is shown here in the upper line. Now, what we want to solve is a multi-objective problem, like optimizing the vector of all these different, all these 7 different objective functions. And this is an interesting point, because when you want to do that, you actually will start to decompose your problem. So we would we are defining a couple of weights that are normalized, and we are just constructing this weighted sum cooperation. So every member of the population has a corresponding weights connected to it. And now we solve the problem simultaneously on the whole population. The population has probably like 3,000 or 10,000 images just by genetic evolution. So we select 2 random indices out of our neighborhood. The neighborhood are these protected neighborhoods where the weighting combination is similar in some sense. Then we generate a new solution by genetic operations, which mean by random mutation and crossover among different candidates from the same neighborhood. And then we update all these solutions and find the non-dominated operator optimal among them. So I think the plot, that the only important plots that need to be understood for MOAT is actually this plot on the top left. We have 7 objective functions. That means our hypersurface of possible solutions that fit our data is 7-dimensional. It's a bit complicated to plot. So we plot it as several projections into the 3-dimensional space. And what you can see here is how different regularization terms and different data terms actually affect each other. We see, for example, we would get F7. F7 is that only the data terms. F7 is best if we also get the total flux right. This makes a lot of sense. F7 is best if we also get the entropy right. But there are actually several terms that are contradicting, like total variation and total squared variation favor some smoothness of the solution, while L1 will favor some sparsity of the solution on the pixel basis, which is actually contradicting the smoothness. So in the case you have these contradicting assumptions, and you want to balance all these contradicting assumptions, the Pareto's front will divide into several clusters. As you can see here from for example, the top left panel, where you clearly identify two different clusters that are not connected. So every cluster represents now a locally optimal image mode. And this is important to note, because every single representant along this Pareto fronts is fitting our data and is a mathematical solution. But they look vastly different. So the front represents the complete range of all possible reasonable image structures that we can fit to our data. And the reason why we can fit all these things to our data is, of course, because the UV coverage is not complete. So they differ by how we extrapolate to the gaps of the UV coverage. Now in imaging, we want to select one objectively best solution, right? We don't want to give someone like 10,000 different images that are all fitting to our data and that all are reasonable in some metrics. We want to come up with the objectively optimal solution that we can use for scientific exploration afterwards. And there are 2 strategies that are just popping up here very natural. One is looking for the closest optimum to the ideal point, and the other one to looking for just the accumulation point, which is the most natural solution among all the solutions computed in the Pareto front. Okay, this is a plot that I tried to make in a couple of minutes. When you have now like y-axis the multi-model function, and x would be the parameter space, when you would do maximum a posteriori or AML imaging, you probably would find the one that is closest to the main peak. With an approximate Bayesian method, you would find like the one that is closest plus some approximation to the to its environment. What Moat is giving you back here are really a set of all the local minima among all the images that we can fit to the data. And we can see when we look at the images in the different clusters, within one cluster, the image features are pretty much the same. But between these different clusters, they are differing a lot. So this was done for the EHT coverage now with closure-only imaging. So when we only do closure-only imaging, the problem, of course, gets more complicated because we just use a smaller number of degrees of freedom. And you can see here all the different clusters that were recomputed. Some of them show some over-resolving structure with talks of too much use of L1 regularization. Some of them are looking like a dirty image, or these double phantom images. There is not a dirty image in this case because we are using closure-only imaging, but these double phantoms that you see here, or these waffle-like structures for the ring example, are quite typical examples of the dirty image counterpart for closure-only image. But the one that we are actually reproducing, or the one that we are selecting with both of the criterions, seems to make sense. Like the blue dotted line is always the one who's closest to the optimum, and the red one is the accumulation point criterion. We also applied it to real data actually, and we see that this looks pretty consistent with what was published by the EHT. There are some image clusters that show a much more crumpy and much narrow structure, but this is clearly not favored by the choice of the regularizers. Okay, once we have done that, we see the forward modeling approach is already flexible enough to just introduce additional parameters, to introduce additional complexity. And one thing that we could look at is movie reconstructions. So we already have this head for the static imaging, the several objective junctionals. Now, when we go for dynamic reconstructions, we just add another one, which in this case is a time dynamic maximum entropy functional that was developed by Alejandro. When we want to do polarization, we do exactly the same. We just add another data term, in this case, the chi-squared to the polarized visibilities, and we would add a couple of specially designed regularization parameters especially designed for the polarized imaging. That would be this Holder-Wardle entropy, for example, or just a polarized version of the total variation. And then you can bring all that together. So now we don't have 7 functionals, now we have 8 for the movies. When you do movies and polarization, it would be actually 11 because we have all these other functions or these other regularization parameters showing up. And what you come up with is a quite high dimensional problem, but we solve it all in parallel. The problem is actually so high dimensional that using or doing a parameter survey is completely futile. It would run on clusters for weeks to months, but with more art, we can actually solve it within a day. So this is, I think, one crucial step to make these things more practical. On the left-hand side, you can see one of the simulations for the EHT or a precursor of the EHT that was done in 2017. And you see, well, even for the very sparse snapshots, so this is a dynamic movie, and we recovered snapshots on a couple of minutes, like in this last case, in this bottom row, you see actually an array only consisting of 2 antennas anymore. We still can get back this kind of ring structure. When we look at the Pareto front, there's actually only one cluster that is recovering that, while all the other clusters are showing this typical, basically just the prior, just the entropy prior that you see here, which is kind of a Gaussian block. And it also works for polarimetric reconstruction. So on the left-hand side, you see all the true image and all the different clusters, and we get a pretty decent image from an EHC coverage of such a star polarized structure. And it's possible, or the algorithm is able in this unsupervised way to distinguish between different magnetic morphologies, as a toroidal or a radial magnetic field. And this is kind of the holy grail of imaging, of course, because now you can bring both together. We have polarimetry, we have movies, we do both in exactly the same way or in a very similar approach. So it does make sense to just combine both. And when we combine both, this is now images taken from the third NGHD analysis challenge. You see that we are pretty well recovering the image structure and compared to ground truth further to recovered on the right. I want to point out that these are very short snapshots. This is a very sparse array. We are trying to do things here at super resolution. We are going for full Stokes polarimetry. We're going for closure-only imaging to get rid of the calibration. So it's really the highest complexity of what we can think of. But because we are exploring the parameter space so globally, we actually find solutions that fit to our data. I want to just take like the last 5 minutes or so to talk about cooperative games, which is a different perspective on actually the same matter. So just to remind you, we still try to study the multi-objective problem, where you want to find all the best compromise solutions among an array of different solutions, among an array of different objective functionals. And we already came up with approximating that with a weighted sum approach. Now, a couple of analytic results here is that the optimal solution of the weighting problem is a Pareto optimal solution under some technical mathematical detail that we're not interested in here. And vice versa, if the multi-objective problem is convex and X star is Pareto optimal, then there exists a unique weight combination such that X star minimizes the weighting problem. Now in VLBI, we unfortunately deal with the fact that our problem is not convex, but it is probably we can extend these theorems to the non-convex part as well. So the idea, the main idea is before we had the idea of, okay, then let's look at all different weight combinations in a smart way. And the smart way was doing that by genetic evolution of the complete Pareto front. And this time we want to find the optimal weights by game theory, where every player in this game, in this cooperative game, is a single objective. And these single objectives are again the data terms or the regularization terms. So we construct a cooperative game with a payoff for any of the single players, and then we construct a payoff for a coalition of them with a symmetric concept. So the symmetric concept means that the payoff of a coalition is does not depend on which players are in the coalition, but only on the size of the coalition. So we would introduce this factor CS, and the CS is nothing else than the discount factor. So what is the benefit of playing together? If now, like the terms 1, 2, 3 are playing together, their payoff of cooperating is higher than the sum of the single payoffs, and the number of how much this is higher is controlled by the parameter C. Now, Shapley values are a way of assigning a unique distribution among the players of a total surplus generated by the coalition of all these players. And this is a very, very genius mathematical concept, which, by the way, actually won the Nobel Prize for economy in 2012, where you try to find some fair contribution of all players, whatever fair means in this way. And this can be related to a fair trade of between different data terms and regularization terms. And how this is calculated, that so mathematically strict, there are actually 3 axioms that need to be satisfied, and then there's only one unique distribution. But here I just show this distribution. We don't have to bother too much with the details, but once we have found all the payoffs, which means we have found all these discount factors CS, that means we can identify a unique weight combination WI to this cooperative game. And now we want to use these Shapley values as regularization weights. So what we are trying to recover, or what we are trying to minimize, is the objective eta C, which is just the sum of WE multiplied with the objectives. Now we are minimizing over all these discount factors in the cooperative game, and the X star actually is the best Shapley optimal solution, which maximizes or minimizes, depends on which perspective you want to use, the weighted sum approach. So this is a different way of thinking about it. Probably by constructing a cooperative game, we can this will just tell us which is a fair trade-off between different regularization and data terms. So let's come to my conclusions. So with the upcoming generation of next generation high resolution, high sensitivity instruments, it's absolutely crucial for us to also upgrade the data analysis techniques to the same standards. It doesn't make sense to build an NGVLA with, I don't know, 260 antennas when you still rely on the same data analysis methods, which has a known bunch of limitations. Forward modeling techniques are performing way superior to clean in a wide range of applications and across the board. So whether you use RML, which I discussed here, whether you use entropy methods, Bayesian methods, or even artificial intelligence methods, they all outperform clean by far. However, they are way less straightforward to apply. They have a steeper learning curve, and the big issue is that we need to fine-tune a range of non-trivial hyperparameters. And it's important to note that these are really non-trivial, because you solve a non-linear optimization problem. So if you just change one parameter very much upstream, it's not that easy to see what is its effect downstream. So the de facto standard for these kind of RML problems is the weighted sum approach. But the weighted sum approach comes with a big problem that you really have to grid search among all solutions. However, there are 2 other perspectives on the problem that provide us with tools and concepts to choose the objectively best parameter combination automatically. One of them were multi-objective evolution, the other one cooperative games. And these algorithms already have a couple of advantages. So they are unbiased. We can do closure-only imaging because we are able to reduce the number of degrees of freedom here, and so to get rid of self-calibration during the imaging, because we are actually exploring globally enough to find all solutions. The thing is unsupervised. As I showed you with MOAT, you can run MOAT, you find the complete Pareto font, and the solution that you will, or the cluster that you will select in the end, it's just selected by this accumulation point criterion or by the closest to the optimum. So there's no human-based decision in it anymore. You can just run the algorithm, you will come up with some solution. And it's the first algorithm that is really exploring multimodality. And this gives us, of course, some estimate of the robustness of the reconstruction. Yeah, well, and I think one of the best demonstrations that this is working, and this is really worth to cover, was the reconstruction of these polarimetric movies, because by now there are only 2 algorithms around that are able to do these movie reconstructions at the event horizon scales. With that, I want to finish, and I'm happy to answer any questions. If there are one.
Thank you very much, Hendrik. Thanks. So let me see if I see any. As usual, you can unmute yourself or just raise your hand if you have any question.
Maybe I can just start asking something. Thank you for the very nice talk. So I understood how the basically the algorithm, the MPIfR would generate these clusters basically of these objective functions. Can you remind me again how then the optimal like cluster is chosen? And because this, if you look at these clusters that are generated, of course, and humans could say, oh, well, they are like non-ring images or so. Like how like reliable would be this choosing, and how objective is the choosing of this like best like cluster of images?
Yeah, and the first point that we have to note is all solutions, all clusters are mathematical solutions. They all get chi-squareds in the range of 1. So this is already the big advantage compared to clean, where you just will come up with some solution, but you don't have any clue on what else could also fit the data. And then when you have this complete range of possible solutions or possible image features that we can fit to our data, we want to come up with something that is, I say it here, objectively optimal. Probably a better formulation would be which is natural. And the way what is natural in principle should be determined by the regularization terms. So you would have, for example, you say the most natural solution among all the solutions that we can fit to our data is the one that has the largest entropy, for example, would be one of the ideas. What we came up here are 2 strategies. It's not clear that these 2 strategies are the only one that you can come up with. There may be more ideas, but these 2 just were like most natural in my opinion. The one is when we look at these different clusters, they don't have the same size. Like there are clusters with only 3 members, there are clusters with 10,000 members. So there's clearly, in most cases, there's clearly a cluster that is absolutely dominating the complete population, which means it's most natural in the case that it's most robust against any change of the parameters. And when we find this cluster, this is what we call the accumulation point. This may be a good idea to draw a choice or draw a selection from the Pareto front. The other one is you can see when we only optimize along F2, then we would find some optimal point only in the direction of 2, or the other data terms or the other objective functionals are put to 0. We do exactly the same with F1. And where these 2 points are actually, where these 2 lines are intersecting, this is called the ideal point. And that's a concept that has been explored for a long time for these Pareto fronts. It's now important to note that there is no image representing the ideal point. It's purely looking at the Pareto front and trying, okay, what is the minimum scoring of F1, what is the minimum scoring of F2, and just writing it in one array. But if this is the ideal point, this is the best scoring that we can achieve if we would fine-tune our algorithm to do that. Then let's look along the Pareto front for the one that is closest to the ideal. That's the closest optimum, and the closest optimum, of course, in principle tells you is nothing else than a least action principle, just applied in this scoring space. But
so if my data became like less sparse, like my recovery would improve, my data would improve, then this curve would sort of like over time, you know, the more I improve my data, the more this curve would approach this ideal point, basically.
Yes. And the more your data improve, the less clusters you will see, because the data will be more constraining, and the image feature will get more robust. Which is why these kind of images tell you something about the robustness of what you actually recover, but you shouldn't interpret this as some kind of Bayesian robustness estimate. that's simply not for what is given you. But of course, if like every parameter combination or every cluster would give you exactly the same image, then you can be very confident in your image structure.
Okay, thank you.
So can I actually have one more question exactly on this slide? Then Alexandros, I will give you the. Here you have so these three are okay. You have the same cluster for these three different models. Are these? What are we really looking? So why crescent disk and ring, and how the model enter in this parameter?
This is a synthetic data test to just demonstrate that it works. So we took a crescent, we created synthetic data with a crescent and recovered it with MOAD. And this is what you can see on the left side. Then we did the same exercise also with a disk and the same exercise with a ring. Why we did that is, of course, the EHT is kind of asking that for us before we show some real data application.
Okay, see, I understand now. Thanks. Alexandros, yes.
Hi again. Thank you so much for the interesting talk. Really cool stuff. So I have two questions. One of is a follow-up on what you said at Felix's question. So in the sense that you shouldn't, so what you said is that you shouldn't take the multitude of these solutions as a Bayesian sort of estimate of uncertainty, more or less. Yes. So can you please also show the picture that you were just showing, where you have the MCMC, like this one? No, the previous one.
This one, yeah.
This one, yeah. So what I understand is that the various clusters tend to accumulate at the optimals of the objective function.
Yeah.
And all the solutions are legitimate solutions in the fact that in the sense that they have chi-squared equal to 1. So they're all possible. Why can't they be sort of interpreted as being samples from the regions around them? Not fully MCMC, but as samples from the extrema, from the regions where you have extrema.
Samples from what? I didn't know.
From the extrema. So where you have clusters where you have peaks, right?
Yeah. So
if you have very well constraining data, you would only have one peak. So you would only have one cluster, correct?
Yes.
So if you have three, so in this case, for instance, you have 3 peaks. So which it would translate in 3 clusters in the F1, F2, F3 vector space. Okay, is that correct? Oh, yeah, right. But then you have many solutions around each of these extrema. Why can't we use these in order to, at least the ones that are in the cluster that we have chosen as a solution, to give us a Bayesian sort of estimate of the uncertainty of our reconstruction? Does the question make sense?
Yes. Yeah, I actually need to think a bit about the interpretation of the complete population that comes out in the end. The point why I say I wouldn't draw a Bayesian conclusion from that is that I'm not sure whether when you would take all the images in one cluster or even across clusters, and you would start to do some kind of standard deviation, I'm not sure that whether this standard deviation is really something that is telling you something. No, sorry, about the uncertainty. And the reason behind that is that what we are changing from one representative of the population to another representative of the population are the parameters. So basically the regularization parameters. In a Bayesian framework, you would probably just explore different image features. But here we are kind of, the thing that is changing are the regularization parameters. And when you want to interpret it in a Bayesian framework, what we actually put on as a prior on this regularization parameters would be uniform, because we are grid searching over them. We just draw them from a grid. And I don't think that this is this does make sense in the Bayesian interpretation. It does make a lot of sense in an RML interpretation, but for Bayesian, I would be a bit more skeptic. Yeah, but it would be, I think it would be absolutely worth to compare samples from an MCMC and more, and to see whether things
Yeah,
are
so
convergent.
I mean, obviously they're not Bayesian samples. I was just wondering whether we can use all the solutions in a cluster as an estimate of the uncertainty, perhaps not in the same sense that it would be equivalent as having been produced from an MCMC procedure. Because
yeah, well, that for sure, because if the data are more constraining, all the samples or the members of the final population will be much more similar to each other.
Have you ever compared the two, like at least do an MCMC sampling at the peak and then compare with solutions? Okay,
No,
that would be interesting to see. Perhaps they can in certain scenario you can perhaps run the MCMC a couple of times, which takes time, but then if you see that they more or less give you a same estimate as a Bayesian one, that would be interesting, because that will give you quite a robust, at least empirical, but robust way to estimate the uncertainty of the reconstruction.
We did run it against Resolve, but Resolve is a software that is not applying a full MCMC. They're trying to save speed by actually approximating the main lobe with a Gaussian distribution, and then you get you're not really able to find all the second order minima, which is more looking for. But we didn't compare against full MCMC yet.
So I have another very short question if no one else has one.
Yeah, go ahead.
So you mentioned wavelets in the beginning, if I'm not mistaken.
Yes, probably in a side sentence.
Yeah, but can you please elaborate a little bit on how they could be used in this framework? You mean like wavelet scattering?
No, I mean, when we have, like, one of our regularization terms is L1, but it's L1 in a pixel basis. You can easily also think about modeling the image by wavelets, and then you would have L1 in a wavelet basis. And this kind of modeling the image by wavelets and then applying a sparsity constraint on it is, of course, studied for a very long time. And this can be interfered with more art, or even with the cooperative games, by just adding another, adding them as another regularization objective to this complete multi-objective approach.
Thank you.
Okay, so I don't see any other hand rising. Okay, then if there are no more questions, let's thank our speaker again. And I will stop the recording here.